become as numerous as the stars on heaven? Or how many stars in the sky can at most be seen with the naked eye? A short contribution to numerical theology. Abstract. Become as numerous as the stars on heaven. Does this recommendation from the Old Testament mean human multiplication without limit? Provided that nature does not decompose into separate entities, but is a connected whole, we identify a relation between the maximum number of stars related to the biblical goal for multiplication, which can be discriminated by the naked eye on the one hand, and the efficiency of human visual perception with respect to angular resolution on the other hand. Introduction. The request to grow and multiply issued in the Old Testament nowadays leads many people to the wrong interpretation of an unrestricted proliferation, whether man in the last 2 millennia complied with the invitation to grow, which probably means something different from purely numerical multiplication, to a reasonable extent, still remains an open question. Assuming that nature does not decompose into individual isolated qualities, but is a coherent and structured wholeness, the metaphor commonly used for numerical growth, as numerous as the stars on heaven, obtains a new meaning. A relation can be identified between the maximum number of stars visible to the naked eye and the properties of the human visual system at the time of the Old Testament. The spatial resolution, differential angular resolution, of the human eye plays the relevant role as the limiting factor. Note 1. In this paper, we are neither interested in the total number of the stars of the universe, nor in the number of actually perceptible stars with respect to their brightness, about 6,000. Assuming further that the visual resolution did not deteriorate since then, no information came down to us from those days, and the success of today's optical measurement technology is not anticipated in the biblical metaphors, we find in the standard literature, reference 1, the value of 0.0172 degrees, approximately 1 arc minute, which is accurately 0.0167 degrees, equal to 1/60th degree for the smallest angular distance between two objects. Then they are distinguishable as two objects under best lighting conditions. At any smaller distance, only one, but brighter or larger, object is seen. Therefore, it is obvious to cover the celestial sphere, more precise its surface observed from the sphere's center in the interior, with a grid whose mesh size is about 1 arc minute. The narrowest grid consists of equilateral triangles. See sketch. A star is attached to each grid point. It follows that two neighboring stars always have minimum distance. Each star belongs to 6 triangles, and each triangle has 3 stars at its corners. Alternatively, one can shift the stars to the triangle centers, then every second triangle remains empty, indicating that exactly half a star has to be counted per triangle. Note 2. In a planar graph with n vertices, k edges and f faces, Euler's polyhedral formula n plus f equals k plus 2 holds. In a triangulation, every face, triangle, has 3 edges. The edges are counted twice, as every edge separates 2 triangles. Then 3f is equal to 2k. And such a graph has only k equal to 3n minus 6 less than 3n edges. Or, alternatively, 2k equals to 6n minus 12 valences. So, not every vertex can belong to 6 triangles, or has degree d equal to 6, respectively. We here ignore this fact, as it is numerically negligible. Calculation. This model reduces the problem to the question: how many triangles fit into the spherical surface? The number is estimated by dividing the total surface of the sphere, 4 pi, by the area of one triangle with about 1 arc-minute side length. All lengths are specified in radians. Let x denote the side length of the triangle in radians. Then the conversion formula applies. X over 2 pi is equivalent to 0.0172 degrees over 360 degrees, yielding x is 3.002 times 10 to the minus 4th. The area of the triangle surface is base side times height times 1/2. Hence, n triangles fit into the surface of the sphere. 4 pi in radians, that is, we obtain n is equal to 16 pi over root of 3 x squared. Results. The maximum number, capital N, of stars distinguishable to the naked eye on the entire surface of the sphere is half the number of triangles, namely capital N equals 161 millions. Hence, from a given point on Earth, about 80 million stars are recognizable, distinguishable in the sky's hemisphere. Final question. What does this figure mean for the number of humans on this planet? References. Addendum 1. With the spatial resolution as an independent variable in arc minutes, the maximum number N of distinguishable stars can be calculated as a function of this variable. See figure below. Addendum 2. There is a remarkable coincidence of figures. The land area of Earth is about 149 million square kilometers, or 29% of Earth's surface. The calculated maximum number of stars is 161 millions. If we identify for a moment the latter figure with the maximum number of humans on Earth, the population density comes out with about 1 per square kilometer. The end.